All right, well, let's go ahead and get started. Last lecture, we talked a lot about unit conversion because those were questions on the homework, and then we also mentioned a little bit about trigonometry. That didn't appear on the last video or anything like that. Today we're going to do more of that. Also, I want to first start off with something called dimensional analysis, which is similar or related a little bit to what we were talking about units, but it will help you when you're doing problems to see if you made a mistake and to quickly be able to see that. And so I'm just going to write this up, dimensional analysis. So if we have a physical quantity, say volume of that, there's usually expressions or formulas written maybe something like this. So for instance, for that parallel pipette shape that we have there, or rectangular prism if you want to be, is a specific shape, the volume of it would be the area of the top times the height. If this volume is independent, it's a real physical thing, and it's independent of the units we use to write it down. So it doesn't matter what the units are that we use to write down the volume, they will always be the same volume. And we can talk about the dimension of this expression as whatever units we use to write it down, it's going to involve a length cubed. So if I could write it in inches cubed, cubic inches. I could write it in centimeters cubed, cubic centimeters, cubic meters, cubic miles, cubic light years. Any of those units I could use to describe the volume of this parallel pipette. So the dimension of this volume, and I'm going to write a little box to indicate dimension, it'll be a length cubed. That means any units I use to write this down, any length unit I use, there's going to have to be three length units to write down the units of this, okay? So that's what we mean by dimension, and I write a little box to indicate dimension of something, little brackets. Since there's really, in this class, there are three fundamental dimensions. There's lengths, and I'll write that as an L when I'm doing this dimensional analysis. There's masses. I'm going to write those as a big M, and then there's times. And I'm going to write these as a big T. The reason why dimensional analysis is useful is that there's a rule that says that if I write out an equation in physics, that every term in that equation has to have the same dimensions. So what do I mean by term? I'll write out an equation. Let's say I'm interested in distance moved. Maybe I'll write this as a D. Distance moved, if you have a velocity and an acceleration, velocity plus 1/2 e squared. You don't have to remember this equation yet. We'll definitely be seeing that again. But these are all the different terms in the equation. Three terms in the equation. All of them have to have the same dimensions. If they don't, then what it would be like would be adding like a length to an area or something similar. And that just doesn't make any sense to do that. It's like adding an apple to an orange. I mean, it doesn't make any sense in an equation to do that. So if I have some dimension here and I'm setting it equal to other things, I can't say like a distance is equal to a distance plus an area. That does not make any sense at all. And so every term in this equation has to have the same dimensions, and you can check that pretty easily and just see if you have an equation that makes sense. If you don't have an equation that makes sense, you made a mistake somewhere. And you can stop at that point and go back and see where that happened. So it's a good way to check yourself on the fly. Let's see if this one makes sense. So this stands for a distance. The dimension of the distance would be a length. This V stands for velocity. Velocity is a distance divided by a time. So the dimensions of that would be a length over a time. And the dimension of acceleration is how much the velocity changes in some time. And we'll talk about this a lot more later, but it's L over t squared. Okay? Are the dimensions of that. So it's velocity divided by a time. All right, let's see if this makes sense. So if I look at the dimension of d, that's L, right? So this every term in this equation should have dimensions of a length, since this term has a dimension of a length. Do you follow? Let's look at the dimensions of this term. Well, that's a length over a time for velocity, and then this t is in time. So this would be length over a time for the v here, and then there's also a time for this t. And so the dimensions of this would be a length. Good. See? So this term makes sense to have it in an equation. How about this one? We don't have to worry about the 1/2 that has no dimensions. So, you know, I just have to look at the a t squared. The acceleration has a dimension, length over a t squared. Then this time squared has a dimension t squared. This t squared cancels with that t squared, and I'm left with dimensions of length. This may not be a correct equation, but it works out dimensionally. Okay? It's not a mistake. Say I gave you an equation like this. Let's say that I called the area of this side of this A2. And let's say I told you that the volume of this shape was equal to A times A2. Maybe divided by 4. Is this equation, can this equation possibly be correct? Let's take a look at it from a dimensional standpoint. So the dimensions of volume, what was that? It's a length cubed. This 4 clearly isn't going to do anything to the dimensions right here, but I can say the dimensions of area, each of those is a length squared, right? So if I multiply 2 areas together, what would be the dimension? Length squared times length squared. Length to the 4th. So here on this side, if I do dimensional analysis, I say I have a length cubed. I'm setting it equal to something with a length to the 4th power. So this cannot be a correct equation. So, not a correct equation. And I just picked out that that's not a good equation. You're trying to mess with me if you wrote that down. Okay? And so it saves you some trouble when you write down a final expression or something. It lets you see what, if you made a simple algebra error, usually is what you catch. Another thing that is that's easy to notice from this when you're doing problems, it's very comforting, it's very easy to plug in numbers that you know right away. Okay? And then forget to carry any units or anything like that. And then when you have to solve for some unknown and you've plugged in numbers and not carrying around any units, you no longer get to be able to do all of this dimensional analysis, because all you are left with are numbers without units on your work. And so it's a lot easier to make a mistake. So one good problem-solving tip is to do everything algebraically. Carry around those symbols until the last step, and then plug in numbers. So do everything, do algebra until the last step. Then plug in numbers. And then this will allow you to check this dimensional analysis thing, whether or not you made an error, a simple error. Also, you'll find you'll save yourselves a heck of a lot of trouble doing this, and also you'll get much more partial credit if you do make a mistake, because it's much easier to see what's going on. All right, that's just a little problem-solving tip. That's a rule of thumb. It's not, every once in a while it is more convenient to plug in numbers at some intermediate point, but that's rare. That's very rare. All right, let's move on to more trigonometry. Okay? Are there any questions on this dimensional analysis stuff? Okay. So, unfortunately or fortunately, we do need a little bit of basic trigonometry for this class. There's no other way around it. But it's not as hard as the word makes it out to be. Usually people get intimidated, and it's really not that bad. So, in this case, we will deal almost exclusively with right triangles. So what's a right triangle?
The right angle.
90-degree angle, yep. And we already know that they obey Pythagorean's theorem. So if I call this side A, this side B, and this side C, that C squared is going to be equal to A squared plus B squared. We already know that. Now, yesterday we mentioned the following. Let's say that this angle, which we'll call theta, is here, and let's see if we can introduce the various trigonometric functions. We can write those in terms of ratios of the side lengths. So, for instance, if this is my angle, which I'll label with this theta, a little Greek letter with a circle with a horizontal line, then sine of theta, what's that going to be? Does anyone know?
B over
B over C. It'll be B over C. And that's because B is the opposite side over, and C is the hypotenuse. So, the opposite over hypotenuse. And you probably have heard, if I kind of underline these these letters, there's a little mnemonic for that, you know. That sign is opposite over hypotenuse. Okay, you probably saw that somewhere. That's how I remember it still. Cosine of theta, what is it?
Adjacent over hypotenuse.
Yep, and so in this case, what would it be?
A over 6.
Over hypotenuse. Which would equal A over C. Good. And then and so, you know, the little mnemonic is if I underline these, you have a cosine is adjacent over hypotenuse, so cop, and then tangent is actually pretty straightforward. It's actually sine over cosine. There's nothing new about tangent. And so if I were to write this out as B over C divided by A over C, if I multiplied both sides by, if I multiplied by 1, C over C, that would cancel that, and that would cancel that. And I would get that this is B over A, which is the opposite over the adjacent. And a little mnemonic for this one. Mnemonic means memorization device, right? O over A, so like that. So SOHCAHTOA is, you know, what, at least what they taught me when I was taking trigonometry. So using these, we can figure out side lengths on triangles if we know any two. Well, if you know any two angles or sides, or any combination of those, you can get everything about the right triangle. Okay. So let's see how that works, and we'll be running into that quite a bit. Let's say I have a right triangle, where this side is 30 degrees, and this length is 2 meters. How could I get, say, this side length? Let me call this B, question mark. Well, what I can see is that the sine of this angle, 30 degrees, that will be equal to the opposite side over the hypotenuse. So that would be B over 2 meters. So if I wanted to solve for what B is, I'll multiply both sides by 2 meters. 2 meters, 2 meters. And I would get that B is equal, you know, it cancels out here, 2 meters sine of 30 degrees. Anyone know off the top of their head what that is? 1 meter. Good. Just so you have a sense, you know, I like to use fairly few angles if I can that I already know the sine of. So sine of 30 degrees is 1/2. Sine of 45 degrees is 1 over the square root of 2. And sometimes that's the same thing as this. If I multiply top and bottom by square root of 2, you get that. And then sine of 60 degrees is square root of 3 over 2. Sine of 90 is 1. Sine of 0 is 0. So those are just things I remember, and they help me just have a sense of how big some looking at. All right, let's ignore that we knew that. Using trigonometry and not the Pythagorean theorem, knowing what that is, can you figure out what that side is? Why don't you give it about 2 minutes and let me know, okay? Work it out on your own. About 2 minutes. You know what cosine of 30 is?
Did you use the calculator in this call?
Oh, yeah. Yeah, you'd be able to. You don't, for the test, you can use calculators. I don't allow cell phones as calculators because you just don't know what people are doing on those. So.
I guess you can get a program or an app for cell phones that it's a graphing calculator.
Yeah, you
and
can.
it can like lock everything else out, like the
I'm not going to
instructor.
worry about it.
Oh, yeah, I would just, I heard of it yesterday.
I bet you can, but then, you know, but then I have to check to see that
That's my phone. Yeah. It calls people, that's all it does.
I like those because they don't break so easily, I don't think.
Well, and they don't call anybody, you don't ask them to call. It's just really handy.
All right, well, let's go figure out what we have here. What did you get?
Cosine of 30 times 2 meters will equal about 1.7 meters.
All right, so 2 meters cosine of 30. Is that what everyone had?
Mm-hmm.
All right, well, let's see how you get that. So I know that cosine of 30 degrees is the adjacent side over the hypotenuse. If I call this A, that would be A over 2 meters. If I multiply both sides by 2 meters, I just get that 2 meters, I get this thing. Okay? Follow that? All right, again, using these angles, we can pretty straightforwardly, with a few simple angles, I'm going to write down what the cosines are. So cosine of 30 degrees is equal to square root of 3 over 2. Cosine of 45 degrees is equal to 1 over root 2. Cosine of 60 degrees is 1/2. And then cosine of 90 degrees is 0. Cosine of 0 degrees is 1. All right. Let's check something here that's good for right triangles. Notice that if I square this, I'll get 3/4. You see that? If I square something, I'll a fraction, I square the top and the bottom. So square this, I get 3/4. Square this, I get 1/4. Add them together, what do I have? 1. 45 degrees, 1 over root 2. If I square this, I get 1 over 1/2, right? If I square this, I get 1/2. Add these two together, squared, I get 1. Same thing here, same thing here, same thing for every angle. And in fact, there's a general rule that, and will occasionally, we might use this, that the sine squared of an angle plus the cosine squared of an angle is equal to 1. And that's actually a consequence of the Pythagorean theorem. We can see it fairly clearly. Let me just show you. Can I erase this? Everyone knows. So imagine that you have a right triangle with a hypotenuse having a side length of 1. Now, I'm not writing any units here. I probably should if it was a physical triangle, but imagine dimensionless triangle. Okay, let's call this angle theta. What would this side length be? Let's call this A and B. What would A be equal to?
A.
Well, I know that sine of theta is equal to A over 1, which is just A. I know cosine of theta, what's that going to be?
B.
B over 1, which is just B. If I square this and I square that and add them together, so A squared plus B squared, that's the hypotenuse squared, which is 1. So that's sine squared theta plus cosine squared theta is 1. You can write this sine squared as rule 2 here. But just remember that the inverse sine of theta is not 1 over sine of theta on your calculator. So it's a slightly confusing notation. I like to use the arc sign for this.
Do what now?
Arc sign rather than inverse signs like this. It's the same thing, but I think it's less confusing to use it to write arc sign as opposed to sine to the minus 1. Don't worry, it's fine. I can figure it. Whichever one you use is okay. All right. Are you ready to move on to something else? Vectors. So we'll get a lot more practice with trigonometry using vectors, so it's going to be okay. Do you want to do any more examples? Are you good?
Yeah.
One more example?
Yeah.
All right, we'll do one more example. Actually, maybe I should do 2 more to be fully complete. So, let's say I have a triangle with this side length being 2 meters. And up here, have a 30-degree, well, let's do a 40-degree angle up here. Okay, I guess that's not very convenient, but you can use your calculator for this. Could you figure out what this side length is and what this side length is? Okay. So go ahead and give that a try. And then we'll go through it. might be a good time to stop this and then I'll start that.
Is this a right triangle?
Oh yes, it's supposed to be a right triangle. That's a very good question.